This is lesson 8, which is going to be an introduction to Boolean algebra. Now, Boolean algebra is named after George Boole, who was an English logician and mathematician. And in 1854, he published The Investigation of the Laws of Thought, in which he gave a mathematical foundation to logic. Now, logic involves, remember, things that are true and false. And in our case, we're going to consider 1 to be true and 0 to be false. So let's look first at one variable theorems. We know, for example, that x or 0 is equal to x. You can check all these by just letting x be 0 or 1, 0 or 0 is 0, 1 or 0 is 1. So this is clearly true, or anything with 0, you get the anything. And x or 1 is equal to 1. If you OR anything with 1, you obviously have 1 whether or not x is 0 or 1. Now, it turns out that there's a principle of duality. We can always change ORs to ANDs and zeros to 1. So here's an AND version. If we change this OR to an and 0 to a 1, this must be true. Well, x OR 1 is equal to x. If x is 0, this side is 0. If x is 1, this side is 1. And x and 0 is 0. If you AND anything with 0, you remember you always get 0. So these one variable theorems are easy to verify. Here's a couple more. X or not x is equal to 1. You see, one of them has to be 1. If one is 0, the other one's 1. So this is true. X or x is equal to 1. They're both 0 or both 1. This is true. And again, the principle of duality says we can change ORs to ANDs and zeros to 1s. So x and not x must be 0. Well, it is, because again, one of them has to be 0. And x and x is equal to x. 1 and 1 is 1. 0 and 0 is 0. Okay, let's look at two variable theorems now. We'll look at the commutative laws, unity, and there are two absorption theorems. The commutative laws simply means that you can commute x and y. That is, x or y is equal to y or x, which by duality, of course, x and y must be equal to y and x. You can easily verify this by just looking at the truth tables. Now, I want to introduce what's called a Venn diagram. These are going to make it easy for you to verify logic identities, Boolean identities. The idea is we'll draw a circle and we'll think of x as being inside the circle as being true, say x equals 1, and outside the circle this is going to be not x, that is, x is false. So x is either true or false, that is, it's somewhere within this, say, square we draw around here. And if it's inside the circle, it's true, we'll call that x. And if it's outside, it's false, that's not x. Now, let's look at, suppose we want to find out what x and y is. Well, we draw two circles. X is true in this circle. Y is true in this circle. So the overlap means that x is true and y is true. So the expression x and y we can consider to be this little football here, you see. So this colored area represents this AND operation, x and y. Now what do you suppose x or y would look like? Yeah, exactly. We just color in both of them. This is all of x. This is all of y. That is, y is true here. X is true here. So in this colored area, including the overlap, represents x or y. That is, either x is true or y is true or both. How about this little colored area here? Well, this represents not x and y. You see why? Not x is everything outside of x. Y is everything in this circle. And the AND operation, remember, is the overlap, where both not x and y must be true. But what happens when you overlap this area outside of x with all of y? Well, you just get the colored area shown here. Now, let's look at this unity theorem. Here's not x and y here. And you remember this little red area was x and y. There's that little football area. What happens if we OR these two together? What are you going to get? Yeah, exactly, you're just going to get y. This is all of y. So x and y, the red area, ORed with not x and y, this area, must be equal to y. You see that? This is called the unity theorem. Now, of course, the dual must be true. If we change ands to ors and ors to ands, well, we change ands to ors here. So x or y anded, or becomes an anded with not x or y, must also equal y. Well, can you see how this works from the Venn diagram? What does x or y look like? That's this, both of them. What's not x or y? Well, not x is everything outside of x plus everything in y. Well, that's everything except this little area here that has the x in it. If you AND that with x or y, that's the overlap. Well, what's the overlap? Well, it's everything x or y except what's in here. Well, that's just y. You can draw it out step by step to verify that. Let's look at absorption. Remember, this red area is x and y. What happens if we OR that with y? That is, we OR it with all of y. Well, we just get y. Since x and y is already inside of y, ORing it just gives y. So this gets absorbed, really. We call it absorption. You see, we just end up with y. Of course, there must be a dual. If we change ors to ands and ands to ors, it must be true that y and x or y is equal to y. Let's see if we can see it. What's x or y? X or y is all of this. Y is all of this. The and is the intersection. Well, the intersection of both of them with just y just leaves y. So again, x or y gets absorbed. Here's another absorption. Let's look at not x and y. Not x and y is this gold color here. What happens if we OR x, that is this, with the gold? So if you add the red to the gold, what do you get? Well, you just get x or y. So x or not x and y, x plus not x and y, that is the gold, is just x or y. What gets absorbed here? Well, the not x gets absorbed. What does the dual look like? Again, change ors to ands and ands to ors. Let's see if you can see this. Not x or y means everything outside of x plus everything inside of y. So again, it's everything except this little area that just contains the x here. And if you AND that with x, so you take everything except this area and you AND it with x, well, you're only left with a little football here, which is x and y. Okay, let's look at three variable theorems. There are associative laws, distributive laws. Look at the associative laws. This means that it doesn't matter where the parentheses is. X or y or z is equal to x or y or z. This is, the dual, of course, is x and y and z equals x and y and z. So again, it doesn't matter which one you do first. You can prove any of these theorems by just making truth tables. If you take x or y or z and first form y or z, you get everything that has a 1, that is everything except this first one and this one. And now if you then OR that with x, so OR this column with x, well, you pick up a 1 here, so you're just left with a 0 here. If you did the x or y first, you get everything that has a 1, that is here, so you have 2 zeros here. But if you OR that with z, over here you pick up this 1, so you end up with this column, and sure enough, this column and this column are the same, so it really doesn't matter which one you do first. Here are the distributive laws. X and y or z is equal to x and y or x and z. That is, we can distribute this AND operation over this OR operation. This looks something like normal algebra. If you think of this as a multiplication, this is an addition, you'd recognize that as being how you could factor out an x here, you see. But the dual must also be true. So in Boolean algebra, x or y and z is equal to x or y and x or z. That is, the OR also gets distributed over this AND. This one, of course, isn't true in regular algebra. Well, you can prove these by just looking at the Venn diagrams again. Look at x or y and z. Well, y and z is y and z, so it's the overlap. It's this football here. And if we add that to x, we get the total hatched area here. Is that the same as the right-hand side? Well, what's x or y? X or y, picture this as, say, being red, these two. X or z, picture these, say, as being green. What's the overlap? Well, the overlap would give you yellow. Where they overlap, well, they overlap just, the AND operation overlaps them, and you're just going to get the same hatch mark you get for the left-hand side. Here's the other distributive law. X and y or z is equal to x and y or x and z. You can see that y or z is all of these two together. And if we AND that with x, we get the area of overlap, and that's just this hatched area. The right-hand side is x and y. X and y is this football. X and z is this football. OR them together, and sure enough, it's the same as the left-hand side. Okay, here's a question. Is this a Boolean identity? Take a look at this and see if you can see if that's a Boolean identity. Well, let's check it out. The way to check these is with a Venn diagram. And you see this, in fact, is one of our absorptions, so it's true. I've actually changed the x and y's. So you don't want to memorize these because you don't know where the x and y's are going to be, or we call them something else. But in any case, we can look at x and not y as the gold area here. Y is now the red, and if we add them together, sure enough, we get x or y. Okay, this shows how Venn diagrams are related to min terms. See, each of these little areas is one of the min terms. For example, this area here is x and y, and not y and z. I'm making the ands just by putting them next to each other and using bars for ors for convenience here. So here we're in x, but we're not in y and not in z. This area, we're not in x, not in y, but we're in z. So not x and not y and z. Up here, this is not x and y and not z. That is, we're only in y, but we're not in x and we're not in y, and we're not in z. This little area here is in x and in y, but not in z. This is in x, but not in y, but in z. And this is not in x, but it's in y and in z. And finally, the little triangle in the middle is in all three. That is, this is x and y and z. So we could ask, for example, is this a Boolean identity? And if you look at this Venn diagram, you see that x and not y and z is this little area. X and y and z is this little centerpiece, and x and y and not z is this. So the left-hand side is the OR, that is the sum of all of these three areas. What's the right-hand side? Well, the right-hand side is x and z. Well, x and z is this total football here. That is x and z. And we're going to add that to x and y. X and y is this football. So you see it is true, in fact. So this plus this equals the sum of all three.